So in the last video, I opened up my new tablet, a Q/7 Stylus. Overall, really good build quality, really good specs, awesome performance. I can basically do anything on it that I could do on my previous laptop and more. However, obviously they needed to cut corners somewhere, and I think I found it. This is the adapter I got with it. It's got the CCC for China crap, only Chinese markings, not even CE, absolutely no UL marking. I'm not gonna stick this into my outlets. This is gonna be torn down and thrown away. And to some extent, I'm kind of disappointed actually that they have such an obviously crappy power supply with what seems like a really high-end product. Just for some general idea of order of magnitude, power supplies are a really competitive business. Like, often non-technical people choose power supplies for like large companies. Like if HP wants to find a new contractor for their power supplies, they write out a request for quote from like 10 different suppliers, and basically the lowest bidder wins. If they don't get really hard specs on what they have to do, they'll skimp on everything just to get the lowest bid. And the difference between the cheapest and the most expensive power supply you can get in a certain category can only be a couple bucks, like actual bill of material. This power supply, I bet it's like $2 or $3 to make. For $4 or $5, they could have a really good power supply. So bad quality power supply is just crappy and will fail. Really bad quality is an outright danger. I once tore down a $4 power supply for a laptop, and it had like little beads of solder running around in the case and causing all kinds of mayhem. It didn't actually fail on me, but it sure as hell will in very short order, and it will definitely do that explosively. So let's open her up. It's ultrasonically welded, so we're gonna have to use the Dremel for this. So what you can do is you can just put your pliers in a corner, and you can kind of feel it out, and you see it's already separated. So then you just grab a nice screwdriver, and oh, actually this hasn't been, this is just clipped. That's actually not supposed to be. So one of the reasons they weld these shut is to make sure that users never get into it without damaging it. Because obviously high voltages inside, this is a hazardous environment, and you do not want to expose even inquisitive users to it. So, well, that's never going to pass UL. I guess that's why they don't have a UL marking. So just looking at it at first glance, the board, it's paperboard, it's crappy quality board, but that's fine. It's one-sided. I mean, this is kind of par for the course for power supplies. Only really high-end power supplies have the nice green FR4 double-sided, but they really try to get every last cent out of it. Another thing that's, I guess it's not too bad on this one. These terminals, they're soldered. They're soldered down actually. So these terminals that go through the other side, they have these little plates here that actually lock into the board, and that they soldered them to so that the board is basically held in by these two solder connections. This would be bad if it's only soldered to the solder sides, to the reverse side of this board. But here they went the extra mile and made it double-sided, and I kind of like this. So let's take a look here. These were the terminals where the power got in. This is obviously some kind of capacitor. I'm not sure if this comes up on the camera, but it says here MPX275 WC something, and then X2. This is an X2 rated capacitor, which means it is a self-healing capacitor. So if this capacitor ever shorts or fails, it doesn't overload your main supply, but it will automatically fix its own internal short. Seems very nice. It's an absolute requirement for capacitors that are mains connected. However, these are very low density. This is probably only a couple of nanofarads. Let me see. 334, so that's yeah, so that's 33 times 10 to the fourth picofarads, i.e. 330 nanofarads. So yeah, not much. So other things we see, this here is a fuse wrapped in heat shrink. There's even an MOV here, which is a nice touch for such a cheap power supply. Big common mode choke, and then it's kind of hard to see, but this block here is a bridge rectifier that feeds directly into this capacitor, which is a Cheng X. 105 degrees, so that probably means 85 degrees. Then on this heatsink, which is a very nice touch, by the way, to have this heatsink. I guess it's a moderate power supply. There's one transistor, so that means this is a quasi-resonant power converter, because for others you need 2 or more switches. Pretty nice looking transformer. This is definitely capable of what is it? 12 volts, 2.5 amps. Yeah, this is more than adequate. We see a nice little optocoupler which does feedback, so this is not just a self-oscillating thing that's essentially unregulated. This is proper regulation. And this tiny little capacitor is the primary low voltage power supply for the primary IC. So that means that we have an auxiliary tap on the transformer, and that also means that there is some kind of dedicated chip. It's not a discrete solution. Then here we can see a little blue capacitor. I'm not sure what that does, but this is the obvious ground, or I guess not ground because it doesn't have a ground connection, but it's a coupling connector, a coupling capacitor. And then on the output, another heatsink with a diode, almost definitely a diode, yep, diode. LC filter, crappy Zunda brand capacitors. I'm not sure why they even bother. Another inductor, probably this is a more dissipative inductor directly to the output. Another little capacitor, and that's it. So one note about these heatsinks. It's good that they use proper aluminum heatsinks. They even have stakes that hold them down, so they're soldered down. They don't just dangle off the transistors. So this is actually what I would consider a medium quality. I would probably not find it too bad to stick this in my main supply, power supply. Been a little bit too harsh based on the outside. However, these heatsinks, the sizing is not quite right. And they're not, like in a proper power supply, the proper way of doing this is to have the transistors facing with their taps to the outside and to have like heatsinks all the way around. And especially the diode, the output diode is going to have the highest dissipation. It's the single highest dissipation component in your power supply. It usually needs the biggest heatsink, and it obviously doesn't here. So I would expect the output stage actually to get pretty hot based on this. Another thing that basically disqualifies this whole power supply is the fact that this is all there is in the plastic case. There is no screening, so there's no little shell around it, there's no plastic insulator around it. Just this. This is a problem because these transistors and this whole arrangement of transistor and inductor, or transformer I guess, because it's quasi-resonant, it's going to cause ringing interference, so a very high frequency noise that is kicked out by both the transformer and the transistor, and this will cause like things like bad cell connection, bad Wi-Fi connection. We'll look at the reverse side, and first thing we see is fortunately they use proper solder mask. It is wave soldered, but it's not manually soldered. I do not see any, oh, maybe these are manually soldered connections, but that's it really. And these are also, they're not too bad. All right, so we're at the input stage here. So here and here is the input connection. Here is this big capacitor, and it has 2 bleeder resistors, which is very good. It means no high voltages will linger particularly long. It's got the solder mask removed here. It doesn't have a proper slot, but it's removed here. And let me see what was here. That's actually just a link. But this here is the fuse. So if it gets interrupted, the solder mask actually has some finite surface resistance. By removing the solder mask, you increase the surface resistance and increase the effective creepage distance, which is helpful for isolating faults. So if the power supply fails and the fuse blows, there is no way that an arc can form. Then here is the common mode choke, which, interesting, I'm not sure why these are here. There's no capacitor there, so for all the world this looks like 2 sets of identical bleeder resistors. Interesting, they could have saved money here. So this is something you often see, these little spark gaps. EEV blog did a post about that, or a video about how these spark gaps work. They're usually found on common mode chokes because if current is flowing through it and a wire fails, the residual magnetic energy will cause the voltage over these 2 poles to get really high, and this way you can dissipate it without too much damage to other things. Then over to the actual guts. I'm not quite sure what is going on, but I can identify some things. This is the driver IC, which is a very, very tiny, like SOT23 6-pin driver IC, but I mean, you don't need that much. You need a feedback input, you need a gate drive output, you need power, ground, and maybe some kind of reference, and that's it basically. So 6 pins probably suffices. Here's the switching transistor with nice isolation slots, not really slots, but at least they kept out the solder mask. Here and here are diodes. I would say that this, because it's so close to this tiny capacitor, this is the auxiliary winding. Yeah, here you go. So this is the auxiliary winding, goes through a resistor, goes through a diode, and then into this small storage cap, which then goes to, I guess here is the power pin. And then this here, this diode is almost definitely a snubber. So I would say that this capacitor that was tucked in here, I'm sorry for lighting situation, it's just impossible to see anything. Yeah, there you go, that capacitor combined with the diode and possibly 1 or more resistors is in a so-called RCD snubber, dissipates high voltage peaks generated by the switching of the transistor. So that's actually pretty nice. You can kind of see like this is the high voltage, so you go, this is positive voltage, this is ground. So on the positive voltage it goes into a resistor, into the diode, and possibly the capacitor somewhere. Yeah, here you go. These 2 terminals are the capacitor, resistor, diode, and that goes into the center tap. So this is one of the this is the switching terminal on the transformer, and this is the drain of the MOSFET. So here we see some 1.5 ohm resistors. So that means that this is the source terminal of the MOSFET, and it goes through these resistors which do current sensing, which feeds back into the into this IC. So I think we pretty much decoded this whole situation here. Now onto the secondary. Very, very simple. Only 2 terminals on the, well, 4 terminals, but 2 by 2. This is treated as ground, and this is treated as the switching terminal. Goes through the diode into capacitor, inductor somewhere, I don't know. I guess it goes into the capacitors directly, and the inductors are actually on the output. There's some LCL filter on the output to reduce the emitted noise. And here we have the feedback network. There is no current sensing as far as I can see. This is some kind of TL431 or equivalent Zener diode reference. And these resistors all couple together with this into the feedback and make sure that the like if the voltage is slightly too high, more current will flow through the reference, and a larger signal will be transmitted to the optocoupler, which signals the primary switching IC to slow down. It's basically how it works. Very linear. So the overall conclusion on this power supply is actually pretty interesting. Build quality and like as far as the performance metrics go, I guess it's actually pretty good. I wouldn't be worried about this power supply exploding or anything. This is one of those situations. It's obviously not compliant, so it's going to kick out noise like crazy. It doesn't have shielding. It doesn't follow best practice and all that. But they kind of they skimped on the good parts, I guess. They make it a functional, reasonable quality power supply that's probably going to last you for at least a year, maybe 2 years. Like it has some things that will never let it go through regulations, but those things are not super important for consumers. So I'm slightly impressed. I would not be too worried about putting this into my mains. Not too worried doesn't mean I'm not worried. So this concludes my two-parter on the Q/7. Overall, good package, very good price performance, and basically no major downsides, no things that you need to immediately change about it to get it to work. So I'm impressed. I'm impressed with the old package. All right, see you later.